This is just a short talk about 32-bit and 16-bit image formats, what they mean, why they're different, and why they're useful to you in astrophotography. So you've seen, no doubt, lots of different image formats, FITs, PNGs, RAW, all sorts of things, and you're probably aware that they all have different bit depths. What does all of that mean? Well, let's start off with the basics. Every image is made up from pixels. And the pixels, each pixel is capable of having one colour. That colour is made up from three numbers. It's the amount of red, the amount of green, and the amount of blue that makes up that colour. Now these are the primary colours for things like monitors, screens, and sensors in your camera, different to the primary colours that you used at school when you were painting, which of course is yellow, red, and blue. When you turn all of those values down to 0, you get a black. And if you turn them all up to maximum, they mix together to make a white. And the maximum value is 255. Now why is it 255? Well, this is due to the way that computers count. They use a numbering system called binary. And it's just like ours, except instead of having 10 symbols for numbers, binary only uses 2 symbols. Zeros and ones, which is what computers think in. And you can count with zeros and ones in much the same way that you do with tens, except that instead of going in a units column, a tens column, and a hundreds column, you go up in twos instead. The counting goes a bit like this. If they're all 0, then the number is 0. 1, 2, 3, and so on, and the pattern continues until you get all the way up to 255, when all of the columns have a number 1 in. That represents all the possible combinations that you can have with 8 zeros and 8 ones in a box. And as you probably know, 8 bits make 1 byte, and you will have heard the term byte, no doubt. And it represents 256 possible binary numbers. That's 0 all the way to 255. So for 8-bit images, you get 8 bits per channel. So 256 levels of red, 256 levels of green, and 256 levels of blue. And that adds up to 3 bytes for every pixel in your image. Now if you work out how many different combinations of colours you can make with 256 levels, you'll find it's about 16.7 million colours, which is more than enough for almost every application that you're going to be looking for images in. So if it's on screen, on print, or whatever, 16.7 million colours is absolutely fine. They do, however, only have a contrast ratio of 256 to 1. So what's the problem? Well, let's take a picture of some stars. Okay, so this star, the double star, Epsilon Lyrae, if I take this photo with ISO 100, I get the values 80 for red, 99 for green, and 202 for blue, and it gives me this nice kind of lilac-y blue colour for the star. That's great. If, however, I turn the ISO up to 200, the gain is doubled, so each of those numbers gets doubled. And what happens is I wind up with 80 doubling to 160, 99 doubling to get 198, and 202 doubling to get 404. Trouble is, I can only go up to 255, so the blue colour gets clipped. It can't go any higher. And you get this colour. Now that still looks like a lovely blue, but if I reduce it down by 1 stop or 1 exposure value to bring it back down to ISO 100, you can see that actually it's a lot greyer than the original colour, and you've started to lose colour information. And the situation, of course, is worse if I go to ISO 400. If I turn it up to ISO 400, all of the numbers clip at the top, and you're left with effectively 255, 255, 255, and it makes white. And again, just to prove, if I now knock this down by 2 exposure values to bring it back in line with the ISO 100, you can see that actually all of the colour data has gone, and that star is now just pure monochrome. So the way to get around that, surely, is to use more bits. So if we go up to a 16-bit image format, instead of 256 levels, you get 65,536 levels, and a stupid number of colours that no one ever needs. So that gives us a bit more flexibility in the brightness levels of the stars that we're looking at, and how much of that range the colour is accurate. So I've made up a little spreadsheet here to compare them. Now this is based on a kind of imaginary thought experiment. This never happens, but let's say in your shot you've got a magnitude 3 star, which is exactly at the top end of the brightness range. So on an 8-bit image it's exactly 255. As you know, the magnitude decreases in brightness by just over 2.5 every time you increase the magnitude number. So a 4th magnitude star is going to be 101, 5th magnitude star is going to be 40, and you'll see very quickly that your 8-bit image format can only really see up to 6th magnitude before the background noise gets in the way. You could probably just about make out an 8th magnitude star, but a 9 magnitude star would be below outside the dynamic range of the image. When you go up to 16-bit, you can see that the situation's much better. So again, we take our 3rd magnitude star at our brightest level, which is 65,535, and we do the same exercise, and you can come all the way down to a 12th magnitude star now before you start to hit the noise, and in theory you could probably even see a 14th magnitude object in that image. Now, even a good RAW file is only 14 bits, so doing the same exercise there, you get from a 3rd magnitude down to about a 10th magnitude on a standard kind of RAW image. So that's one problem, is that it doesn't give you a very big dynamic range to enable you to see really, really faint objects, at least not with any clarity. The other problem is when you come to process the images afterwards. And this is a slightly contrived example, but it shows the point. So a section of the Orion Nebula here has this particular image histogram. So this histogram represents the brightness levels of the image and how many pixels have that brightness level. Now when we make the image brighter by stretching, what we're effectively doing is stretching this histogram up. But you'll see you get this posterization effect, where the levels become more and more obvious as you stretch it up. And this represents itself in the histogram by a series of blank sections in the histogram. So let's look at posterization close up. So in this little row of 6 pixels, let's say the kind of real value, if the starlight was recorded exactly as it hit the sensor would go up to a value of 6.4 for this pixel, 6.7, 6.9, 6.2 and so on, and you would get this range of colours. However, sensors can't do that. Remember, 6 is a very low number, so we're talking about very dim things. What actually happens is as the photons hit each pixel, they're filling up the bucket, and if they can get up to the next level, they'll go to a 7. But none of these are quite bright enough to get it up to a 7, and what your sensor sees, instead of all this lovely detail, is just the same value. And then when you come to stretch it, let's make the maths easy and times it by 10, you'll see that they still all have the same value. And that's where these gaps come from, is because you're taking a 6 and you're stretching it up to 60, you're taking a 7 and you're stretching it up to 70, and there's still nothing in between. The ideal situation would be this, where we capture the exact value that we want to come in, and then when we stretch it, we can multiply by 10, and we've got this extra precision to allow us to still see the detail. So to get to that ideal situation, we need 2 things. One is we need an image format that includes a decimal point, and 2, you need to capture data with more precision than your sensor can handle. We're going to talk about each one of these. So how do you get a decimal point? Well, The way we've talked about using bits to make numbers so far is something called fixed point numbering system, and it only creates integers. That's whole numbers. You can, however, make a floating point number using exactly the same number of bits. And in this particular case, you can see that I have one bit here which is used for the sign, so you can have plus or minus. You have this here which represents the number, and then you have this which represents the scale of the number. And this is like when your calculator tries to display a number that's too big for the screen, and it might say something like 1.737E11. And E just means times 10 to the power 11. In other words, you're 11 columns away from the decimal point. Well, in binary it's 2 to the power, but the principle holds. And that, instead of 65,000 levels, effectively gives you 4 trillion levels, which is a bit more useful. Now, as it happens, we don't tend to really use the 16-bit float option. 16-bit image files are generally the fixed method. If we're talking about a 32-bit image, however, we're talking about using the floating point method. And that gives you a range of levels that might as well be infinite. 10 to the 38 is just a stupidly big number, and 10 to the minus 38, that's where you get the decimal point and numbers smaller than 1. So we've got our image format with the decimal point. How do we capture data with better precision? Well, we stack. All astrophotographers know about stacking. So what's actually happening when we stack? Well, let's take this row of 6 pixels again. Remember, the real values are here coming in. Now, it doesn't always just capture a 6. There's a thing called photon noise, which means that the light coming from the star is statistical. Sometimes you'll take a shot and you'll get a few more photons, and sometimes you'll get a few less. And so what happens is on each sub-image, you will get a slightly different coloration of pixels, looking like this, because some will have a value 6 and some will have a value 7. And when you take them into a stacker, you average those numbers out. And by averaging them, you bring in the decimal point and you start to get the extra precision. And you can see here that even with only 3 subs, you're starting to get a lot more detail come through on the image than you would have done in the previous example where they were all just 6. In a more detailed example, in this GIF I've got here of different subs taken of the same star, you'll see in this red circle there is a star, but you can only see it on some frames, and that's because its level is so similar to the background noise level that sometimes you can see it and sometimes not, because of the statistical nature of the noise in the image. So actually, noise is our friend in this particular case. If we look at this graph, the blue line here represents the value of the background pixel, so one of these pixels here, on each sub. So each one of these columns is a separate sub. And you can see that each one is slightly different value. The star pixel, on the other hand, is represented by the orange value. And you can see again that they're different values. And sometimes, like here, the noise for the background means that the background is brighter than the star. And other times, like here, you can see that the star is brighter than the background. Now, when we do our averaging in stacking, you can see the dotted lines. And this is a rolling average of all of the values so far. So you can see that actually, over time, and fairly quickly in fact, you start to get a separation between the star and the background. And that separation gets more and more precise until as you add more and more subs. So this is where you get your precision from. And you can see here that this is 6, and the one below it is for argument's sake, about 5.5. You can't really tell from the axis. So there's a very, very small difference between those two. But because we're now storing that as a floating point difference, when you stretch that image, you're actually getting a much more accurate result, because it's scaling up numbers with a higher precision. So, making 32-bit images is relatively trivial, to be honest. You start off with your raw format, you bring them straight into DSS or whatever stacker you're using, you stack them and it outputs a 32-bit image with all of those nice high precision average values. You then process your image, stretch it, do whatever else you want to it, and you're left with a beautiful 32-bit image at the end. Trouble is, no one uses 32-bit images, can't do much with it, can't post it on Facebook, anything like that. So, we need another stage in the process to bring it back to a normal image. So the last stage in the process is that you have to take this histogram that you've got for your 32-bit image, which could potentially be quite a wide histogram compared to your normal 255 levels, and you have to squash it down to fit into a low dynamic range for your final image format. That process is called tone mapping. Now I've just put up a little Photoshop dialog here because there's two key ways of doing that in Photoshop. I'm sure there are other ways in other software as well. Exposure and gamma is the one I use most, and basically that gives you the most accurate representation it can make of what you're actually seeing on the screen. But you also have local adaptation, and local adaptation can really help you to bring out some of the dimmest objects, but it's got a lot of settings and it's very difficult to tweak to make it look right, so it can be your friend or it can be your enemy. The point is once you've done that, then you can get to the point where you have a final image. So we take our raw images into DSS, that produces a 32-bit image which we edit. Then we also take our edited 32-bit image and we tone map it down to an 8 or 16-bit. And in Photoshop this happens automatically when you change the image mode from 32 back to 16. It gives you all those options. And then you're left with an 8 or a 16-bit image that you can use in the rest of the world, which is a JPEG or a PNG or whatever your preferred format is. So 32-bit pros and cons. First of all, it's a high precision image format, that's good. It's editable without loss, there's no posterization, you can edit it to your heart's content with impunity. However, it's not directly usable and it makes much bigger files. And I just thought I'd finish by giving you a real world example of the storage and how big those files are. So on my Nikon D600 I have a 24 megapixel camera and it produces 12-bit NEF files. Each one of them is typically around about 26 megabytes. So if I make 20 subs, that gives me 520 megabytes. It's half a gig of data. Then I have my calibration frames. So after I've done my stacking with my darks and flats and all that kind of stuff, I wind up with 4 calibration frames. I have my master dark, master flat, master dark flat and master bias. They are 47 megs each, so give or take that's another 200 megs. I'm now up to 0.7 gigs of data for one image. Now my 32-bit stacked image is a whopping 248 megabytes. I don't tend to keep those because the next thing I do is I bring it into Photoshop and I save the Photoshop file. So the stacked image, once it's in Photoshop, I tend to get rid of it, but I do save my image list in the stacker so that I can restack it again if I need to. Now PSDs from Photoshop vary and it depends a lot on how many extra pixels you've got in there. So if you're using a lot of star masks or gradient correction masks or things like that in your Photoshop file, then you're going to wind up with a very large file. My largest one to date is 1.8 gigs. So if we are adding all of those together, my one image can basically require 2.5 gigs of storage just for all the data to create that image. Contrast that with when I tone map it out to a PNG. PNG from that image set is 27 megabytes, so it's 100 times smaller than the total set of data that I've got recorded. JPEGs even better. I mean, that is a huge saving, down to 0.3 megabytes. So it seems like a lot, but if you've got good data in your subs, and you've done some good editing that you want to maybe revisit another time, you really need to store all this stuff too. Brilliant. Thank you. It's been a pleasure talking to you. I hope you found this useful.